Hello, this is a follow-up video to solving equations with logarithms. The previous video we solved the equation above, example 1, with log base 7. And we ended up also finding that there were some extraneous solutions. We will run through a couple more examples with solving equations with logarithms, but this time we'll be using a natural log. So for the very first problem, we'll keep it a little bit simpler where we're solving the equation. So solve for x. And so the example that I will go over will be the ln of 9x minus 7. When does that equal the ln of 5x plus 33? So again, this natural log has an argument that is actually a linear value on the left and a linear value on the right. I apologize for all the excess noise. I have kids at home while we're doing distance learning from home, so sometimes they're talking. I need to set the insides equal to each other because at this point we've got a natural log equaling a natural log. And so I have 9x minus 7 must equal 5x plus 33. Again, since the log is the same base, the natural log base e equaling the natural log base e, the insides must be equal. That's the only time when these two will actually have the same value. So now, solving this equation for the unknown value of x, I subtract 5x, and then I'll also add 7 in the same move, and to figure out what does actually remain for this particular problem, and I end up with a 4x over here and 40 over on the other side. Then continuing to isolate the variable by dividing both sides by 4, I get only one x value, and that one x value is 10. Now, just because we only get one x value doesn't mean we shouldn't check our answer, because it could be that there is an extraneous solution. Most likely there would not be because I am not squaring anything, but we might want to check that. So I'm going to go ahead over here and just check that the left and the right hand side do equal each other. So here is my check. Is the ln of 9 times 10 take away 7, does that really equal the ln of 5 times 10 plus 33? So here we've got the ln of 90 minus 7, wondering does that equal the ln of 50 plus 33? And so here, this is the ln 90 minus 7 is 83. And does that really equal the ln of 50 plus 33 is 83. So check. That solution did work out. The next example that we will go over will also be a natural logarithm problem. So the next example, I'll move over to the side here, is example number 3. All of these examples are solving for x. So again, if you're asked to solve for x, and this time we've got the ln of 60 minus the ln of 4 equaling the ln of x squared plus 2x. So we've got a pretty complicated looking logarithm on the right there. That's a quadratic logarithm. And over here, we actually have just logarithms that don't vary at all, but I can consolidate these two together. I see, again, a subtraction problem here, so I can condense these two together, condense using the quotient property of logs, the quotient property of logs. So condensing those two together under one logarithm, it would be the natural log. And now, again, inside it becomes 60 divided by 4. And then I close my parentheses, and then this is again equal to the ln of x squared plus 2x. Now, simplifying that, that's just 15. So this must mean, therefore, right? Like if the natural log equals the natural log, which it does, this is telling me then that 15 equals x squared plus 2x. Again, I've got another quadratic. I know looking at this, I need it to equal 0 in order to use one of my tools of factoring. I also could complete the square if we wanted to do that on this particular problem, but because the leading coefficient's 1, I'm just going to try to quickly factor this. So subtracting 15 from both sides, subtract 15, and what do I have left? But 0 equals x squared plus 2x minus 15. This positive coefficient tells me that I happen to know that 15, which has multiples of 3 and 5, again, the multiples are 3 and 5 or 5 and 3. If you see that this is positive here, that means that the 5 must be positive. In fact, the 3 there is negative. But when I use zero product property, again, I like to abbreviate that as zero product property. If two things multiply or even more to 0, then one of them must be 0. So our solutions here are x equals negative 5 or x equals 3. So there are some of our answers. Also, it would make sense to check these answers to make sure that the left and the right-hand side do really equal each other. Now, the interesting thing is because this is being squared, that might make this actually both of those valid answers. So let's go ahead and check the value of x equals negative 5 first. So if we have the ln of 60, take away the ln of 4, I can still consolidate those two together. And over here, I have the ln, again, of negative 5 squared plus 2 times negative 5. So this becomes the ln of 60 divided by 4 again, equaling the ln. But negative 5 squared is actually a positive 25, and then take away 10. So here we've got the ln of 15. Does that really equal the ln of 25 take away 10? Yes, it does. So check. That solution is valid on that side. If I do the same thing and I check the other solution, check x equals 3. So again, we've got the ln of 60 minus the ln of 4. Does that really equal the ln of 3 squared plus 2 times 3. So simplifying and condensing the log over here using the quotient property, I'm wondering, again, all of these are checks. Does the ln of 9 plus 6? So over here, this is again the ln of 15. Does that really equal the ln of 9 plus 6 is 15? So both of those solutions are valid solutions. I would love to go over an additional problem. If you feel that you have learned the material enough, feel free to end the video. You could pause it here, come back later and watch it, but I'll run through a couple more examples. So, example number 4. So this example, however, is going to look a little bit different. So here I will have the ln, now a log not equal to a log. So this is again a different scenario. It will be a log equal to a number. So if I have the ln of 4w plus 9, and when does that equal 5? Well, this is a situation where, again, it is not a log equaling a log, but it is a logarithm equal to a number. So it's important to recognize that this is really the same thing, right, as the log base e of 4w plus 9 equaling 5. And I can rewrite this, in equivalent exponential form. And if I do that, that will enable me to solve this. So if I rewrite, this is the same thing as e to the 5th, right? E to the 5th equals 4w plus 9. Now, e to the 5th is just a number. E to the 5th is a number that is going to be irrational. I can hit second ln, gives me e, but I want to figure out what is e to the 5th. E to the 5th is 148.413. But I can at least isolate this for now, the w being what I'm isolating. This is the same thing as e to the 5th minus 9 divided by 4 equaling w. So that is my final exact answer. If I wanted to have an approximation for what w approximately equals, I again could use that e to the 5th value that I have right there. I could take away 9 from that, divide it by 4, and then figure out that it is approximately 34.853. 3. I could store that in an alpha character, and I could go back and actually check this. So if I check my original answer, the ln of 4 times that second answer value plus 9, this should be pretty close to 5. So when I hit enter, I get exactly 5 because, again, I use my calculator's more exact approximation, which had like 10 digits compared to what I recorded down here. And so I was able to check my answer. I will go through a couple of more examples, and I will end the video after perhaps 2 more examples only. So here is example 5, when we have this time a very different looking problem. This one will say e to the x equals 21. This is kind of like 2 to the x equals 12. We've been solving a lot of problems like this. But this is not 2 to the x, this is 2.718 to the x equals 21. So how do we solve this? In general, I would say, well, we take the log of both sides, right? And so if we take the log of both sides, right, what if we just took the natural log of both sides? The natural log is log, base e. But if I took the natural log of this side and I also took the natural log of the other side, what would I have left? So again, I'm taking the natural log of this side and the natural log of the other side. Well, if I use my power property to knock this down here, this is really the same thing as x times the ln of e, right? So that's what's inside here. And then this equals ln of 21. Well, what is the ln of e? The ln of e is the log base e of e. So ln of e is 1. And so that's why this is so beautiful just to take the natural log of both sides, because this piece right here is just 1. Again, times x equals the ln of 21. So therefore, again, our x value is the ln of 21. Again, you do not have to put the argument in parentheses. I do sometimes and then I don't. So that's, again, how we undo this particular problem. To solve for the x, we take the log of both sides. Let's do another example kind of like this. So this example is very similar, example number 6. This time, though, it'll be a little bit more complicated equation when it becomes negative 2 times e to the x plus 14 equals negative 6. So again, here we've got an equation. It happens to be an exponential equation, and I need to solve for x. So what do? We isolate it. We get everything else away from the term that has the x. So first step, subtract 14 from both sides. What do I have remaining after that is negative 2 times e to the x equals negative 20. Next thing is to divide both sides by negative 2 to get e to the x equals 10. And in the spirit of that, what we just did in the previous problem, if we take the natural log of both sides, the ln of e to the x and the ln of 10, we use the product property of logs to knock this down. This becomes x times the ln of e equals the ln of 10. And as a reminder, this is 1. Again, because why? It's the log base e of e. And so that is 1. So in this case, I would have x times 1 equals the ln of 10, or again, my final value is the ln of 10. Now, some of you are probably wondering, like, what? This is so bizarre. It just means log base e of 10. So e to what power gets you a 10? And so it's thinking about 2.71 times itself. How many times is going to get you to 10? I could check my answer in my calculator. So in my calculator, if I put in negative 2 times e to the ln of 10, so ln of 10, and then after that, I needed to add 14. I'm expecting to get an output of negative 6. So I'm just plugging in my answer, and what do I get out? A negative 6. My calculator confirms that I did my algebra correctly. Let's do one final problem together. And that problem is just, again, to recognize that the logarithm, that is the natural logarithm, is just a function. So I'm going to use my calculator here to show you a couple of things. I've plotted in my calculator, if you can see here, a couple of different functions. My first function is going to be e to the x. It's just an exponential 2.718 raised to the x power. It's exponential growth because your multiplier is larger than 1. Its inverse equation is the natural log of x. So I'm plotting that. And just because of the fact that we also know from chapter 5 that functions and their inverses are reflections over y equals x, I went ahead and put that into my calculator. If I hit graph here, you can kind of see how, again, both of these are just functions. The blue function here is e to the x. So if I think about it again, this is just e to the x. It's an exponential growth curve. And its logarithmic inverse function is the natural log. If, again, I wanted to figure out like some of these values here, like what happens when I hit second calc and then I figure out the value for the function when we put in the value of 1? Well, the value of 1 should get me out e on the blue curve. Why is that? Because it means e to the first power. And so there is my value of 1. If I'm on the other curve, I think if I hit trace and then perhaps I could jump to the other curve and now hit second value. If I put in the base now, I should get out 1. Again, because that's how all logarithms work. When you put in the base, so again, second e to the first power, I should get out 1. Do I get out 1? No, I don't, because it's actually on the other graph. So that's actually one of the challenges I have to work out with my TI-84 calculator is how do I get the value on this purple function? That was giving me the value on the blue function. So again, when you put in the value of e, that was what its output was. So this concludes my video. I realize that this was a little bit longer, but I hope that it was helpful just to not be intimidated by the number e. 2.71. E, again, the base of the natural logarithm. An irrational number, a very powerful number for compound interest.